Hi, everyone. I'm Yang, and I'm going to tell you about dynamic Maxflow via dynamic interior point methods in this talk. To start, let me define the maximum flow problem. In the maximum flow problem, we have a directed graph with a source S and a sink T. And the question is, what is the maximum number of edge disjoint paths from S to T in this directed graph? For example, in the graph depicted here, the maximum flow is 3 because there's 3 edge disjoint paths and you cannot find 4 edge disjoint paths. As mentioned in the title, in this talk, we're going to focus on dynamic maximum flows. That is, to maintain a maximum flow, maybe with approximation factors, on a graph that undergoes edge changes. This is quite a challenging problem, which I'll explain some of the reasons later. And in this talk, we're going to focus on a restricted version, which is the incremental setting. This means that the graph will undergo only edge insertions, no deletions. However, we are still going to think about the case where the graph is directed and the edges might have capacities that are larger than 1, even though this example will depict unit capacity graphs. So in this example, let's start with an initially empty graph that's undergoing edge insertions. We want to maintain the maximum flow. So we add an edge, maximum is still 0, add an edge, still 0. Now this edge has caused the max flow to be 1. After some more edge insertions, the max flow has now become 2. And now after a few more insertions, the max flow actually is now 3, but we have to change the routing of the flows to achieve that. So you can see there's some challenges in solving this problem, which I'll go over. Instead of the incremental setting, there are other dynamic settings of the Maxflow problem, or in general, graph algorithm problems. In the decremental setting, there's only edge deletions that are allowed. And in the fully dynamic setting, both edge insertions and deletions are allowed to the graph. Because Maxflow in any dynamic setting is already quite a challenging problem, we're going to focus on the incremental case, which has the nice property that if the flow we initially have is feasible, then because we only have edge insertion, when it is inserted, the feasible flow is still feasible. It can't become unfeasible. We're just going to focus on the incremental setting in this work. As I was mentioning, it's been quite challenging to obtain any improvements to dynamic max flow. The best known runtimes in previous works were limited to unit capacity graphs and incremental settings, or undirected graphs, but the approximation factors were very large. They were m to the little o of 1. While in this work, we're going to focus on 1 minus epsilon type approximation factors. Precisely the best results in these regimes are a 1 minus epsilon approximation with runtime m to the 1/2 times epsilon to the minus 1/2 in a unit capacity incremental graphs, or in undirected graphs, an amortized n to the 2/3 runtime, or m to the little o 1, but once again, only in unit capacity graphs. Additionally, there's a hardness for solving Maxflow in some settings due to the online matrix vector conjecture. In particular, for the even simpler problems of incremental and decremental bipartite matching, if you want to solve them exactly, it requires omega of mn time. This justifies working with approximation factors for when we're trying to solve dynamic max flow, and we're going to focus on 1 minus epsilon type approximations in this work. Despite all these difficulties towards solving max flow, there are some recent lines of work that give us hope of overcoming these difficulties. One line of work that seems very clearly relevant is recent advances in solving max flow and min cost flow in static settings in almost linear time. Additionally, there's been a lot of recent work on designing dynamic algorithms for graph problems specifically incremental or decremental matching type problems that use optimization methods such as multiplicative weights or entropy regularized optimal transport. So these lines of work give us hope for giving improved runtimes for dynamic Maxflow. To start with this first line of work, the main result that was shown in a very recent work is an exact algorithm for a min cost flow on a graph with polynomially bounded costs and capacities that ran in m to the 1 plus little o of 1 time, almost linear in the number of edges in the graph. At a high level, this algorithm solved Maxflow based on a procedure called an interior point method, which is a method for solving linear programs. By applying this interior point method, the algorithm solves min cost flow in m to the 1 plus little 1 iterations, each which takes m to the little of 1 amortized time. Each iteration involves solving a dynamic minimum ratio cycle problem. And to solve it efficiently, the work designed a dynamic data structure for solving this problem. In the min ratio cycle problem, the problem is to maintain under changes to G and L to maintain a small approximation, m to the little o of 1, to the following problem: min overall circulations delta of the ratio between G dot delta and L delta 1 norm. So by solving this problem dynamically over m to the 1 plus little 1 iterations, under changes to G to L, this work was able to give an algorithm that solves min cost flow exactly in almost linear time. Now, the other line of work is graph algorithms based on optimization. So, there's even classically been algorithms for dynamic problems that use the multiplicative weights procedure. And these works often focused on incremental or decremental matchings or positive linear programs. Basically problems where you can design algorithms that involve the multiplicative weights method. Recently, these bounds were tightened and extended where several groups designed algorithms for incremental or decremental matchings based on the optimization methods of entropy regularized optimal transport or dynamicizing multiplicative weight methods. This begs the very natural question of whether these interior point methods that have been useful for static Maxflow can be used in the context of dynamic algorithms to give improved runtimes. This seems more difficult because the interior point method is kind of a more complicated procedure, while most multiplicative weights is much more combinatorial. So our main result in the context of these is that we give an algorithm that solves incremental Maxflow on directed graphs with polynomially bounded capacities that maintains a 1 minus epsilon approximation and has amortized runtime n to the 1/2 plus little o of 1 over epsilon. The algorithm succeeds with high probability against adaptive adversaries, where here adaptive adversary means that the adversary can see all the randomness that's used in the algorithm. Now, when we started this work, we weren't necessarily interested in adaptive adversaries, but we actually don't know a better bound, even if we assume that the outer updates to edge insertions to the graph are from an oblivious adversary. We don't know how to get a better runtime. And this is a very interesting open question. In terms of techniques, one key definition that we use in this work is we define a problem which we call thresholded min cost flow or thresholded max flow. Given this thresholded max flow problem, which I'll shortly describe, we show that it naturally interacts very well with the interior point method of the almost linear time Maxflow algorithm. In fact, the updates to the interior point method can be amortized over edge insertions readily, and it still takes about m iterations. And finally, because of this oblivious versus adaptive adversary issue mentioned above, we can't use the data structure of the almost linear time Maxflow algorithm exactly, and instead we adapted to work against fully adaptive adversaries to achieve our runtime. Okay. I'll start by describing the first piece, which is the definition of the threshold and min cost flow problem. In this problem, once again, we have an initially empty graph G that's going to undergo directed edge insertions. And we're also going to have a threshold F star, which is at most 0. Now, over time, the graph will undergo insertions of directed edges with costs and capacities. And the capacity constraint will be that the flow on edge E, FE, is between 0 and its upper capacity, UE. The question is, determine the first time when the min cost circulation has cost at most F star. Recall that a circulation is a flow with 0 net demand and satisfies the capacity constraints. And the cost of a circulation is the inner product of the cost vector with F, which is sum over E of CE FE. Given this, the definition makes a lot of sense because the cost of the min cost circulation is not increasing. We can just assign a 0 flow on the incoming edge. It maintains that it's a circulation and the cost hasn't changed. So that means that the min cost circulation value will cross the threshold F star at exactly some fixed time. And our goal of the problem is to exactly determine that time. Beyond working for Maxflow, which I'll describe shortly, this problem has other very interesting applications. For example, the incremental cycle detection problem, which is to decide the first time when a directed graph has a cycle under edge insertion, or the directed ST shortest path problem, even with negative edge lengths in graphs that undergo edge insertions. So given this definition, the more general version of the Maxwell result is that we give an algorithm that solves incremental threshold and min cost flow on directed graphs with polynomially bounded costs and capacities. We determine the time that the threshold crosses F star exactly, and the amortized runtime is n to the 1/2 plus the low of 1. Once again, we succeed against adaptive adversaries that see all the randomness in the algorithm, and we don't know a better bound against oblivious adversaries. To see why this implies the Maxwell result, note that you can reduce max flow to min cost flow by adding a T to S edge of cost -1. This way, the min cost circulation will have cost negative of the max flow. And we'll set the threshold F to be powers of 1 plus epsilon so that we can maintain a 1 plus epsilon approximation where we have O tilde of epsilon to the -1 different thresholds. And thus, if we solve each threshold problem in parallel, then the amortized runtime is n to the 1/2 plus little o of 1 over epsilon time for a 1 plus epsilon approximation. In the remainder of this talk, I'm just going to talk about the dynamic L1 interior point method, and then a little bit about the adaptive data structure, and then I'll conclude. We'll start by discussing a little bit about the interior point method from the almost linear time Maxflow paper. In this setting, we have a cost vector C, capacities U, and a threshold F star. In this paper, they maintain the log barrier potential function. Phi of F is -20m log of C transpose F minus F star, plus the sum over all edges of a logarithmic barrier on these edges. This barrier will have a log of UE minus FE term, where UE is the capacity of edge E, and a log of FE plus delta term, where delta is going to be chosen to be 1 over poly m, a small positive constant. I'll explain the use of delta shortly. Let's make a few simple observations about this potential function. The first is that for the zero flow, the potential is at most m log m. So the potential basically starts at m log m. Now note that the first term, the log C transpose F minus F star term, helps us to determine when the cost of our flows cross the F star threshold. In particular, if there is a flow where C transpose F, the cost is the most F star, then the first term could go to -infinity. Now the second term, the sum over edges E of the log barrier, enforces a version of the capacity constraint. It enforces that FE is between UE and negative delta. Note that this actually differs from the supposed capacity constraint of 0 and most FE and most UE. However, this negative delta can only affect the min cost flow cost or the flow value by poly m times delta. So if delta is 1 over poly m for sufficiently large poly m, then it doesn't actually affect the value by very much, and that's acceptable. Now, let me just discuss a couple more aspects of the interior point method. For example, how do we decrease the potential function to eventually get to nearly optimal max flow? Now, notice that if the potential is the most negative 200 m log m, then the cost is the most f star plus 1 over poly m. Additionally, the potential is the most initially m log m. The main interior point theorem shown in this work, in the previous Maxflow work, is that the interior point method satisfies the following properties. The first is that if there is a feasible circulation with cost underneath the threshold, then the min ratio cycle problem has quality at most minus 110 for the vectors G and L that are input. Additionally, for these vectors G and L, if we find any circulation delta whose ratio is the most negative kappa, then there's a way to add a multiple of the circulation to decrease the potential by omega of kappa squared. So for example, if kappa is a polylog approximation to the best quality and the flow is feasible, then we'll decrease the potential by at least a polylogarithmic amount. Because the potential starts at m log m, and we want to decrease to negative about m log m, and the number of steps will be almost linear in m. Now, this is all still in the static setting, but the extension to the dynamic setting is actually just a simple observation. All we need to understand is how the potential changes under an edge insertion. And it's actually easy to see that the potential only increases by log m after an edge insertion. To see this, let E be the new edge that was inserted. Let's set the flow on edge E to be 0. Note that the leading term doesn't change because the cost of the flow doesn't change. And the second term changes by negative log UE minus log delta. Now, if UE is an integer and at least 1, the first term is going to be negative. And because delta was chosen to be 1 over poly m, the second term will be negative log delta, which is O of log m. So over the m edge insertions of the algorithm, the potential will only increase by O of m log m, which was the initial potential anyways. So in this way, the total number of iterations doesn't actually increase. It'll still be almost linear in m. At this point, I wanted to give a high-level overview of what the dynamic algorithm for threshold and min-cost flow would actually look like. For the purpose of this, let DS be a data structure that solves min ratio cycle against an adaptive adversary with m to the little of 1 approximation factors with an amortized runtime of t. Let's initialize the flow f as 0, and when an edge E is inserted, we're going to first set the flow to be 0 because we don't need to do anything. And now we're going to execute the following loop. While we're able to find a circulation whose ratio is the most negative kappa, where kappa is some m to the little o of 1, we determine this by querying the data structure. We're going to update f to f plus some eta times delta. This will induce updates to G and L, where G and L are the vectors there. We're going to pass the updates to the data structure. And finally, if the flow has potential the most negative m log m, we'll return it because we know that we're done. Now, otherwise, we're going to loop back up and query the data structure to decide again whether there's a circulation with a good cost and continue. If at any point we can't find a circulation anymore whose cost is sufficiently negative, most negative m to the negative little of 1, we're going to determine that there's no feasible circulation by the interior point theorem previously that has a cost in most of the threshold. There can't be, or else we would be able to make progress. And then so we terminate that phase, and then we take the next as insertion. Okay. That's how the algorithm works. Note that this algorithm will terminate in m kappa to the minus 2 log m iterations, each of which was cost amortized runtime t, because we're going to make a query to the data structure and updates to the data structure in each of those cost time t, and we do it once per while loop, And each while loop will decrease the potential by about kappa squared. At this point, I just want to say a few words about the adaptive min ratio cycle data structure before concluding. In the dynamic min ratio cycle problem, the goal is to design a data structure that on a graph G with a vector G and a matrix L supports the following update and query operations. In the update operation, the goal is to, for an edge E, change the value of GE or LE. And in the query operation, we want to return a delta, which is an m to the little o1 approximation of the following ratio: min over circulations of the inner product between G and delta over the L1 norm of delta. In the previous work on almost linear time Maxflow, the paper designed an algorithm that solves the problem against oblivious adversaries with m to the little o of 1 amortized runtime. However, an oblivious data structure does not actually suffice for our setting, but also not even for static Maxflow. The reason that the oblivious data structure does not suffice for static Maxflow is that the outputs of the data structure might affect the future inputs, in particular, the updates to G and L. To handle this issue, the previous paper defined a new stability notion called hidden stable flows. And one way to word this is that in the static Maxflow setting, you can show that for the fixed optimal flow F star, it's true that for delta is F star minus F, that the ratio is good. And that gives us a little bit of control on what the adversary can do in terms of changes to G and L. And in the static setting, this notion can be combined with the oblivious algorithm plus some additional tricks to give an algorithm, a data structure that suffices for static Maxflow. However, in this setting, this does not work, even if the edge insertions are oblivious, because something breaks down in trying to adapt the hidden stable flow strategy to our setting. And thus, we settle for making our data structure fully adaptive at the cost of a worse runtime. Now, to describe a little bit about how the data structure works, I'm going to give a pictorial description of the data structure in the almost linear time Maxflow paper. In this setting, we start with the graph G, which we call level 0. And in the first level, we're going to build forests F1 to F O tilde K. And in each of these forests, we're going to find G contracted by the forest. And this graph has about M over K vertices. The key part now is to sample down to O of log n of these forest branches and ignore all the rest. We're going to build a spanner on each of these forests and then recursively process the spanners. Two key points are that the level I graph has about M over K to the I edges. There's a factor K decrease. However, at the very bottom level, because of the sampling, the number of graphs we're maintaining is O of log n to the D, which is M to the little o of 1. To point out the key place where this data structure is using some type of oblivious notion strongly, it's in the step where O of log n branches are sampled. Now, to change this data structure, instead of sampling the branches, because we want to have an adaptive data structure, we're just going to maintain all of them. I'm going to keep all of them instead of sampling down to O of log n. This way, the level I graphs still have M over K to the I edges. However, on level I, there's now about K to the I graphs that we have to maintain. We were going to trade off to make these about equal. So K to the D is about going to be root M. And this is going to lead to the M to the 1/2 plus little of 1 amortized runtime. Now, I had promised N to the 1/2 plus little of 1, but this can be achieved by applying a sparsifier, a spanner at the very top level to reduce M to N before doing this recursive scheme. To conclude, we gave an algorithm that solves dynamic thresholded incremental min cost flow and Maxflow in directed graphs with amortized runtime N to the 1/2 plus little of 1. And through a standard reduction, this gives a 1 minus epsilon approximate Maxflow in amortized time, n to the 1/2 plus little o of 1 over epsilon. In terms of techniques, we defined the thresholded problem. And then after that, we showed that the interior point method of the almost linear time Maxflow work can be amortized or dynamicized readily. And also, we showed how to make the min-range cycle data structure of that paper succeed against adaptive adversaries. The most natural open question from this work is to improve the amortized runtime to n to the little o1 over epsilon against oblivious adversaries. We don't know how to do this. As I was saying, our runtime against oblivious and adaptive adversaries is the same. Now, this dependence would be nearly optimal on both m, n, and epsilon. So I guess the m would be almost constant, but the epsilon to the -1 would actually be the optimal dependence. And that's all I had to say. Thanks.